Hey everybody, we're going to get into some serious applications now. So this first application is about the instantaneous rate of change. You should recognize that. We've already talked about it. So when we talk about instantaneous rate of change, we're talking about rate of change, which is what you see in this box here. So this is the rate of change between 2 points in time or two locations or there's different things it could be. We're going to look at some examples. And then as you let h go to 0, this rate of change ends up allowing you to find the rate of change at a particular instant of time, which is why we call it the instantaneous rate of change. But then this limit we've actually defined to be the derivative of our function. Now notice this is at a particular point, so we're going to be talking about applications at a particular time or a particular situation, moment in a time period. And here's our first example. The area A of a circle, so let me draw you a circle. So here we have a circle. Is related to its diameter. So remember, diameter is the line that goes all the way across. Okay, so area is how much is inside, and the diameter d is how far across you are. So the area of a circle is related to its diameter by this equation. So this is just a formula for area, where you guys might be used to seeing r. We're doing it in terms of diameter here instead. So normally it would be pi r squared, but here, because we have diameter, we have to divide by 4. How fast does the area change with respect to the diameter when the diameter is 10 meters? Okay, let me try and explain this to you. If this diameter were to increase by, let's just do a little tiny bit, just this much here. So notice it's a very small increase in diameter. Does that have much effect on the area? Well, let's consider what the new area would be. So remember, if you increase your diameter by just a little bit, how much did that increase our area by? This is a terrible circle, but best I can do. So notice, it's a little tiny change in diameter, but it's actually a good chunk of area that we've increased by. What if we changed the diameter by even more? What if we had an even bigger diameter? What if we did like this much? Both sides added a little bit. Does that change your area of your circle? It actually changes it by quite a bit. It's still just a small increase in your diameter, a little bit on each side, but your area on your circle, look at how much more you have. All of this around here is extra now. This wasn't there to begin with. That's a lot of area. So what we want to do is we want to talk about the relationship between when diameter changes a little bit, how much does the area change in respect? To do that, we talk about the rate of change of the area with respect to the rate of change of the diameter. This is just another notation for what? The derivative. Remember, this is the derivative of A with respect to D. If we take the derivative of our area function with respect to D, what would we end up with? That's going to give us the relationship between if diameter changes a little bit, then area changes this much. Let's see what it is. So we're going to take the derivative of pi over 4 d squared. Pi over 4 is a constant, so or constant multiple, so he's just going to chill out. What's the derivative of d squared? Now d is operating like your x or your t would be operating. He is your variable. So pretend he's x squared. What would the derivative be? Well, that would require us to use one of our rules. Which rule? Power rule. Power rule says the power comes down, times d to 1 power less. So it's now just d to the 1. We can simplify that. We can reduce the 2 and the 4. And we end up with pi over 2 times d. What does this mean? Well, if d changes, let's see, how fast does the area change with respect to the diameter? So if the diameter is at 10 meters, so d is at 10 meters, okay, and then your area, how much will it change by? If the diameter changes just a little bit, at what rate is the area correspondingly changing? Well, let's see. Plug in 10 to your derivative, so pi over 2 times 10. We can reduce that. 10 divided by 2 would be 5 and 1, or 5 pi. And our units are meters, and this is area, so this is meters squared. Okay, so let me see if I can help you understand what this is saying. If our diameter is at 10 meters. And our area, we want to know how fast that's going to change. This is telling us that if our diameter is just a tad bit more, but just a little bit, small change is all we're talking about when we talk about derivative, then our area is going to be 5 pi, will increase by 5 pi. So if diameter increases by just a little bit, area is going to increase by 5 pi. That's quite a bit per every little that the diameter increases by. On the other hand, if our diameter was only 1 meter, what rate of change would our area see? I want you to see the difference here. So take your derivative, plug in 1 meter. That would just be pi over 2 meters squared. So when your diameter is smaller, 1 meter, a small change in your diameter will only increase the area by a smaller change. The bigger your circle, the bigger your diameter, a very small change in that diameter will cause an even larger change in your area. The bigger your circle gets, the bigger your diameter gets, the bigger the change you would see in your area if your diameter were to change. So hopefully that helps you understand what's happening here. We can talk about area, we can also talk about volume, we can talk about surface area, and there's going to be 2 other applications we're going to see in the next videos. So make sure you understand each one of these. They're very important. If you need some more help or need me to clarify anything, reach out, ask me questions so I know where I can help you all understand. So study hard. I'll see you in the next video.